Hi Math 30-1s. Today we're going to take a look at graphing log functions. Okay, so remember that log functions are inverses of exponential functions, so reflections of exponential functions in the line y is equal to x. So just keep that in mind as we are working through today's lessons. So first thing that they ask us to do is explore the value of b in y equals log base b of x. So we'll investigate how changing the value of b affects the graph of log base b of x. Notice that every graph of this form, okay, must pass through the point 1, 0, okay, because log base b of 1 is equal to 0, right? So remember that when I'm doing this, b to the exponent of 0, okay, must equal the argument, which is 1, okay, and anything to the exponent of 0 is 1, okay? So that means all of the x-intercepts are going to be at 1. Part 1. The graph of log base 3x is shown. The graph passes through the point 3, 1 because log base 3 of 3 is equal to 1. So again, remember, if that's confusing to you, that this is an x-coordinate, this is a y-coordinate. So when I go to my graph, I replace the x-coordinate with the x-coordinate and the y-coordinate with the y-coordinate. And then again, from what we've learned, 3 to the exponent of 1, okay, will equal the argument, which is 3, okay? So it works out when I also convert it into exponential form. Okay, so again, they're just stating some facts there about the graph and showing that it satisfies the equation when I substitute those points into the equation. Now, in each of the following, complete this statement and sketch the graph on the grid. Use a graphing calculator with these window formats, okay? And we can do that to double check. We're not going to. We're going to do it without a calculator. And again, we want to always be able to do that. A calculator is a nice way to verify or check our answers. But for the most part, we should be able to graph these without our calculators. Now, again, just as a review, when I take a look at those window settings, okay, remember that the first number is always our min. Okay, the second number is our max, okay, and the third number is the scale that we're dealing with, okay, and the same goes for the y settings, okay, min, max, and scale, okay, in case you are confused as to what those numbers represent. So first thing, our first graph here, it says y is equal to log base 10x, and it's going to pass through what, 1, okay? Well, again, this value that they give you is the y coordinate. So that would be like me going over and replacing that y with 1. Well, I know now that when I go into exponential form, that would be 10 to the exponent of 1 will equal the argument or the x value. So 10 to the exponent of 1 is 10. So that has to be the x coordinate. So that log base 10 of x is going to go through 10, 1. So go all the way to 10 and then up 1, okay? There is the point it's going to go through, and we have also determined that it's going to have an x-intercept at 1. Again, if you're confused about that, remember, how do we find an x-intercept? You let y equal 0. So you go into your equation over here, let y equal 0, log base 10 of x. I want the x-coordinate, so convert into exponential form, okay? And that's how you would calculate what the x-intercept is, okay? So I'm going to have this logarithmic graph, okay, that passes through the x-coordinate, or sorry, x-intercept of 1 and through the other point at 10, 1. So you can see that when I graph it, okay, again, it comes up by this asymptote. Once it goes through there, okay, it's going to get through this point 10, 1 like so, okay? So there is my graph, and I can always label it, okay? And I'll label it obviously as log base 10 of x, like so. Okay, next question, right? They now want me to graph log base 1/3 of x. So I use the same basic principles I did in the first one. Again, they want to know it passes through what, 1. Well, again, this is a y value. So if I went and replaced this with 1, you would have 1/3 to the exponent of 1, which is 1/3. So this is going to pass through 1/3. Sorry, that's a terrible 3. 1/3, 1. And that is the x-coordinate. Okay, so when I do that, okay, I find 1/3, 1. So that's going to be here. So what that means, okay, is that it is going to be coming down, okay, this direction. It has to, okay, in order to hit that point and go through this x-intercept of 1. Okay, so when I do that, okay, the graph is going to continue through, okay, like so, okay, and go right through here, okay? So what I'll tell you right now, okay, and this is, I'll label it first, log base 1 over 3 of x, is that when I take a look at this base of 1 over 3 of x, okay, that is the reciprocal of 3. So those two graphs actually end up being reflections of each other in the x-axis. So I know that this point went through, log base 3 of x went through here, which was 9 comma 2. So this graph is going to go through 9 comma negative 2. Okay, they're reflections of each other in the x-axis when the bases are inverses of each other. Okay, so next, the last one here is going to be log base 1 over 10 of x. Well, based on what I just told you, this and this one in number 1, okay, should be reflections of each other, okay, in the x-axis. So I know that that log base 10 of x went through 10 comma 1. So this graph will go through 10 negative 1. It'll also have an x-intercept at 1, okay, like all of these graphs do. It's going to pass through the point 1 over 10 comma 1, okay, and again, it's going to be coming down in this direction. So 1 over 10 comma 1 through that point, okay, and again, it's a reflection of 10 to the x, so it's got to come through this point right there, okay, like so. So log base 1 over 10 of x. Okay, just like that. Now in B, what they have us do is they have us graph the following: log base 5 of x and then log base 1 over 5 of x. So again, first thing I notice, okay, the bases here are 5 and 1 over 5, so they're going to be reflections of each other in the x-axis. Now when I go and graph log base 5 of x, just like the previous examples, it's going to go through the point 5 comma 1, okay, so I can label that point now 5 comma 1, and also I know that base of 5 is closer to 3 than it is to 10. So when it comes up through that x-intercept of 1 and goes through that point of 5 comma 1, it's going to be closer to log base 3 of x than it is log base 10 of x, okay, so here's log base 5x, and then when I reflect it for log base 1 over 5 of x, again, it's going to go through the point 1 over 5 comma 1, okay, so 1 over 5 comma 1, okay, somewhere in here, okay, goes through that x-intercept, and then a reflection of log base 5 of x, okay, so through here, okay, and then down through this point. Again, it's going to be closer to log base 3 of x than log base 1 over 10 of x, so it'll be down here, like so, and again, that will be log base 1 over 5 of x, okay. Now, if you run into trouble, okay, with any of those graphs and you don't understand how I graph them just by doing without a calculator, remember that on your calculators, you can always graph a function by, for example, if I take this one in B, I could graph this as log x over log 5, right? And the one beside it, I could also graph, if I wanted to graph this as a second function, I could graph this as log x over log of 1 over 5, okay? So always an option if I want to use my calculator to verify a graph that I've created, or just to look at it so that you get the basic ideas and their characteristics. Now, we're going to complete the table based on all of those graphs that I just graphed above in part 1A. So fill in the table. Now, when you take a look at all of those graphs, you'll notice that they never cross over the y-axis. So the domain for all of those graphs will actually be x is greater than 0. Okay, notice I do not say or equal to 0. Okay, they are greater than 0, and then we always state that x is an element of the real number system, okay, or an element of the real numbers, okay, however you prefer to word it or say it, okay. So they share domain characteristics. The range, okay, the same for all of them as well, okay. It can be anything in terms of real values for the y. So y is an element or a member of the real number system. Okay, so that holds true for all of those graphs. The x-intercept, if you take a look at the x-intercepts, they all went through 1. Okay, the y-intercepts, they didn't have any. Okay, they never touched or crossed the y-axis. The asymptote, okay, the line that the graphs approach but does not touch, well, that's the y-axis, okay? So the y-axis has an equation of x is equal to 0, Okay, so I'll just fill that in. And underneath or above, okay, you can say that that's the y-axis, just so that we're aware that we're speaking of the same thing, but they'll usually ask for an equation. So we'll say x is equal to, as opposed to just saying the y-axis. And again, what's the x value when y is 1? Okay, well, it's going to be the base. So 3, 10, 1 over 3, 1 over 10, and then in this case, b. So remember, when y is 1, if you go to any of these equations, this is like, I remember saying 1 is equal to log base 3 of x. So 3 to the exponent of 1 is x. Therefore, 3 is equal to x. Okay, so that's how we're calculating that value. Okay, next page. So just some characteristics and questions about them, what we noticed from the calculations we did and the graphs that we created. So how do the graphs of log base 3x and log base 1 over 3 of x compare with each other? Okay, well, as I stated, they are reflections of each other in, on, or over the x-axis. Okay, so the reflections in the x-axis. Part E, how do the graphs of log base 10 of x and log base 1 over 10 of x compare with each other? Okay, well, exactly the same thing. They are also reflections of each other in, on, or over the x-axis. Okay, and then again, just to restate the same thing, the graph of 1 over bx compared to the graph of log base b of x, those are a reflection in the x-axis. Okay, that's what they are. So hopefully that's making sense. Okay, and we've made that point enough times that now that's kind of sticking in your brains. Okay, when the bases are 1 over each other, then they are reflections of each other in the x-axis. Now, from the transformation unit, okay, yes, we're going back to that. We know that when we reflected something in the x-axis, what we did is we replaced y with negative y. Okay, we took the y coordinates and made them negative. That reflected the graphs or the points over the x-axis. Now, it says starting with y equals log base b of x, make this replacement to determine the equation that's for a graph that's reflected in the x-axis. So they're saying start with this. Y is equal to log base b of x. Now, do the replacement, take out y and put in negative y. So negative y equals log base b of x. And now re-isolate y. We don't want it to be negative. So I end up with y is equal to negative log b of x. Now, what that means is that I actually now then have two ways, okay, of writing the equation of a log function that is reflected in the x-axis. And that's why they take us to this little box down here, okay? These first ones are what we learned on the first page, okay, reflecting graphs where the bases are 1 over each other. And then I just created another one, which is negative log b of x. So they can write it in either form. You have to know both of those, okay? It's not okay just to know one and not know the other. They will present questions to you, okay, and they being me, okay, on a test or an exam, the diploma, if you were going to be taking it, they will ask you to do that in both ways, and you'll see that in your homework assignments and textbook work if you go in there to work on some questions. Okay, so both of those forms we need to be aware of. Next example, it says, if log base 4x is equal to 8, state the value of log base 1 over 4 of x. Now, I should be able to kind of figure this out, okay, without doing a calculation algebraically, but let's just take a look at what they're asking me to do. So if I did something like this, I had log base 4 of x, okay, and it was like this, and it equaled 8, right? Okay, log base 4 of x is equal to 8. Okay, I know that that's the value here. Okay, there's going to be 8. Okay, like so. Okay, there is 8. Now, if I take that graph, okay, and I take the base 4 and I make it 1 over 4, well, it's going to be that graph reflected over the x-axis. So that graph, if I reflect over the x-axis, is going to do this, and now be shaped like this, okay? Well, if my point on the first graph was 8 and I reflect it over the x-axis, that point is now down here, okay? And the answer will be negative 8, okay? So that should be the value that we are after here, okay? Negative 8. So it says in B, prove this result by converting to exponential form. So here's what happens. I take the graph and the equation that they gave me, log base 4 of x is equal to 8, and I'm going to convert to exponential form. So I'm going to go 4 to the exponent of 8 is equal to x, okay? And that's all I do at this point. I then go to my log base 1 over 4 of x, like so, okay? And I want to know what that equals. Well, let's say I don't know what it equals, so we do what we did previously in this chapter, and I just make it equal an unknown variable, okay? I will also convert to exponential form, so 1 over 4 to the exponent of v will equal x, okay? 1 over 4 is the same as 4 to the exponent of negative 1, so there's my 1 over 4, it's still to the exponent of v, equals x, so this will be 4 to the exponent of negative v equals x, okay? Well, what do you know? That x actually equals 4 over 8, doesn't it? Or 4 to the exponent of 8. Okay, and I got that from the first graph. So now that I have powers with the same base, I can say therefore negative v is equal to 8. So therefore v is equal to negative 8. Okay, and that's what we decided it would actually equal when I took a look at it graphically in part A as well. Okay, so hopefully those calculations make sense. You're able to understand the algebraic when it meshes up with the graphical just above it, okay? So you will see questions like that in your homework, okay? And again, if you have trouble with them, just refer back to this part of the video, okay? Or again, send me a picture of the assignment and I will get back to you with some helpful hints, some instruction, and some calculations. Next page, okay, part 2. It says, the partial graphs of log base 2x, log base 4x, and log base 8x are shown, okay? And again, they show them to us on the grid. Again, what you'll notice is that the larger the base, okay, 8 compared to 4 compared to 2, the larger the base, the closer it is to the x-axis, okay? So it says complete the following statements, and this is part A. Log base 2 of x, so I'm working with this graph right now. Log base 2 of x passes through the point 8 comma what? So again, remember, this is an x. They are looking for the y value. So I would go into the equation and say, okay, y is equal to log base 2 of, and replace x with what? So when I do this, if I convert to exponential form, it'll look like this. 2 to the exponent of y equals 8. Okay, well, 2 to the exponent of y equals 2 cubed. So guess what? Y is equal to 3. So that's what this point is right here. And you should be able to see that now. If I go to 8, 5, 6, 7, 8, 1, 2, 3, okay, there is that point, okay, which we just found, 8, comma 3. Okay, so hopefully that made sense how I did the calculation, okay, and how that point is located on the graph. The next one, 2, okay, a little trickier, right? Log base 4 of x passes through 8 comma what? Well, again, this is an x coordinate. They're looking for the y. So if I go to the equation, it would look like this. Y is equal to log base 4 of, and for 8, it's substituted in for x. So you will go 4 to the exponent of y is equal to 8, okay, like so. So now what we can do here is, if you're really good with mental math, you'll be able to figure out that that's going to be 3 over 2. You take the square root of 2 and then you cube it. If not, you convert to powers that have the same base. So 2 squared, there's your 4 to the y, would equal 2 cubed. So you have the same base, 2y equals 3. Equate the exponents. So y is equal to 3 over 2. So there's the value of the y, 3 over 2. Okay, now 3 over 2 is 1.5, so that graph is going through 8, 5, 6, 7, 8, and 1.5 right there. So there's the point 8 and 3 over 2, okay, which I'll just put as 1.5. It's easier to write on the graph, okay? And then lastly, okay, the third one, same basic idea. This is the x. They're looking for the y. So you would substitute 8 in for x. Well, in that case, the base and the argument are the same. Okay, so the y value has to be 1, and you'll see that that graph does go through 8, comma 1, which is right there. So 8, comma 1. Okay, so that's all that they're asking us for in part A. Okay, find the y coordinates when x is provided for us. You can do it algebraically. In this case, it wasn't too bad to look at the graphs they provided. But sometimes, like for the red one, the 8 and the 1.5, or the 8 and the 3 over 2, I can't really assume that that's 1.5, so I have to do the algebraic calculation to confirm that. Okay, so just make sure that we're okay with that. Now, in part B, it says the graph of log base 4 of x is a vertical stretch of the graph of log base 2 of x. Okay, so they're saying start with log base 2 of x and you vertically stretch it to get log base 4 of x. State the stretch factor and complete the statement. So log base 4 of x equals what? What kind of stretch? Log base 2 of x. So what I would do is, remember, when I'm stretching vertically, okay, so when I am going to stretch vertically, okay, you are going to be affecting the y coordinates. So in this case, I would be comparing 3 in 8 comma 3 to 1.5. Well, 1.5 is half of 3, isn't it? So that means it was a stretch by 1/2. You took all the y values and you multiplied them by 1/2. Okay, starting at log base 2 of x and ending at log base 4 of x. Okay, in C, okay, it says the graph of log base 8 of x is a vertical stretch of log base 2 of x. So again, in this one, I'm starting at log base 2 of x and I want to end up at log base 8 of x. So again, compare those y values. So this time it's the 3 and I'm making that 1. Well, what did I do? I divided it by 3, so that means it's the same as or equivalent to multiplying it by 1/3. Okay, so that is the stretch factor for each of those. So that's the question they ask. What's the stretch factor? So in B, it's 1/2. Okay, and the stretch factor in C is 1/3. Okay. Now it says use the result above to determine the transformation which would map the graph of log base 2 of x to log base 64 of x. Now remember, log base 2 of x is going to be further away from the x-axis than log base 64 of x. Now, in order to explain this to you, I'm going to go back to B and C and show you something that we didn't talk about as I was showing you those initial calculations. Okay, and here's what it is. Let's say I talk about, for example, C. Okay, I went from log base 2 of x to log base 8 of x. Now, what you'll see is log base 2 of x I'm going to leave alone, but log base 8 of x I can go log base, and the number 8 I can write as 2 cubed. Okay, 2 cubed is 8, and then with an argument of x. The stretch factor is going to be 1/, that exponent, once I've created bases that have the same value. Okay, so I have 2 cubed, the stretch factor would be 1/3. Okay, that exponent. Using that idea, let's move on to the next one. They're saying I want to go from log base 2x to log base 64 of x. Well, the key is, can I write 64 as a power with a base of 2? And you can, right? 64 is 2 to the exponent of 6. Therefore, the stretch factor, okay, would be 1/, that exponent. So the stretch factor is going to be 1/6. Okay, so to get log base 64, you take log base 2 of x and stretch it vertically by 1/6. Okay, so it says this is an example of the general rule. Okay, the transformation which maps log base b of x to log base b to the exponent of n of x is going to be a stretch factor by 1/n. Okay, so you want to have those logs with the same base. And the second one, okay, when it is written as a power, a base and an exponent, it's 1/, the exponent. That's the stretch factor, okay, that you put in front of the original log function. So let's see if we can take that idea now and discuss these next questions. Describe, the transformation which would map the graph of log base 3 of x to log base 81 of x. Now remember, you always want to be sure of which graph you're going from and which graph you're going to end up at. So if I do log base 3 of x in blue, okay, it's going to be like this. It's going to be further away, okay, from the x-axis when I compare it to log base 81 of x, right? Log base 81 of x is going to be way down here. So as a vertical stretch going from the blue to the red, you're not going to be stretching by a whole number. It's going to be a fraction. Okay, so what I do is I take a look at their bases. Okay, again, remember, this is a base of 3, and this 81 I want to write as a power with a base of 3, don't I? So that's actually 3 to the exponent of 4. So that means that the vertical stretch then, so it's a vertical stretch by a factor of 1 over 4, okay? And that's what they do. They say log base 81 of x is equal to 1 over 4, or a vertical stretch of 1 over 4 on the graph of log base 3 of x, okay? Next example, okay? So this one you want to be really careful, maybe even put a star beside this one, okay? And the reason being is this is what happens in this question. They want to go from log base 16 of x to log base 4 of x. This is log base 16, okay? It's closer to the x-axis than this graph is, okay? So this time I am going to stretch by a whole number because I'm going from the red to the blue. So again, what I do is I take a look at those bases. Here it's 4. This is 16, which is what? 4 squared, isn't it? So that means, okay, that I am actually stretching by a factor of 2. I take that log base 16 of x, stretch it by 2, double its distance, okay, and I end up at the blue graph this time. Okay, vertical stretch by a factor of 2. All right, moving on. Next, it says if log base 5 of x is equal to 6, state the value of log base 125 of x. So when I see that, okay, similar to a question we did a little while back, this is 5 and this is 125, okay, which can be written as 5 cubed, okay? That means it's going to be a vertical stretch by a factor of 1 over 3, okay? So vertical stretch by a factor of 1 over 3. So I'm just going to write that here. Vertical stretch by a factor of 1 over 3. So if I take that first graph, okay, log base 5 of x, okay? So I'll do this. This is log base 5 of x, okay? And the value is 6, okay? So there's the y value at 6. If I stretch that vertically by a factor of 1 over 3, well, it's like dividing it by 3, okay? So take this and take 6 divided by 3, it's going to end up being 2, okay? That's your answer. So this graph is going to end up being down here, okay, like this. That's that value, because you take this down this direction, you multiply it by 1 over 3, okay? Multiply the y values by 1 over 3, which is like dividing it by 3, okay? So it's going to have a y value equal to 2. Now, they're saying prove that by converting to exponential form. So again, very similar to what we did about 2 pages ago. I go like this. Log base 5 of x equals 6. Okay, I just restate what they gave me in part A, and then I convert into exponential form. So 5 to the exponent of 6 is equal to x. Okay, log base 125 of x equals an unknown variable. I don't know what it equals. That's what I'm after. So what I do is I convert also to exponential form. 125 to the exponent of v is equal to x. Okay, like so. 125 is actually 5 cubed. So there's your 125 to the exponent of v equals x. So 5 to the exponent of 3v is equal to x. Well, again, x from the calculation I did over here actually equals 5 to the exponent of 6. So now I've created powers that have the same base. I can equate the exponents. 3 to the exponent of v is equal to 6. Okay, and 6 divided by 3 is equal to 2. Okay, same value I got up above when I showed you the calculation or what was happening visually on those graphs. Okay, all right, we're getting there. Further transformations of log functions. We use the knowledge learned in transformations to compare the graph of y equals log base c of x to the following. So again, A is your vertical stretch, B is your horizontal stretch, H is your horizontal translation, left and right, K is your vertical translation, up and down. We use the letter C to represent the base to distinguish it from the letter B, which is the horizontal stretch, okay? So that's the only reason they use C there. So again, they say the graph of log base 3 of x is shown. Write the transformation associated with each of the following and sketch the graph on the grid. Okay, so the first one, the difference is obviously this 2 here. So how did that get there? You would have replaced y with 1/2 of y. And when we do that, we know that that is a vertical stretch by a factor of 2, okay? So by a factor of 2. So I take the graph that's provided for me and I stretch everything vertically by 2, multiply the y values by 2. Okay, that x-intercept is not going to go anywhere. I can take this point at 1, 2, 3, comma 1, and it'll go to 3, comma 2. Okay, and then I can take the point at 9, comma 2, and it'll go to 9, comma 4. Okay, so that's enough points, and you will see that when I come through those points, okay, it is stretched vertically by a factor of 2, same basic shape, okay, but it has to go through those points that I have created by multiplying the y values on the original graph by 2. Okay, and then I label it y is equal to 2 log base 3 of x. Okay, vertical stretch by a factor of 2. All right, next one. So in the next one, what's happened is it was log base 3 of x. It's now x minus 2. So you have replaced the x in the original function with x minus 2. That is a horizontal translation 2 units to the right. Okay, so you're going to pick up all the points on the original function and just move them 2 units to the right. So your x-intercept at 1 will now be at 3. Okay, and again, just pick up as many points as you can see on the graph, okay, and move them 2 units to the right, okay? Now, the other thing is that, remember, I had a vertical asymptote on the original graph at x is equal to 0, which is the y-axis. That also gets moved 2 units to the right. So for this graph and this graph only, that's why I'm doing it in red, okay? That asymptote also gets moved 2 units to the right. So there's your vertical asymptote that your graph can't touch, okay? So the graph would come up very close to that, go through these points, like so, okay? So there's your graph for y is equal to log base 3 of x minus 2, okay? Everything 2 units to the right, including that asymptote. And then the third one, okay, in this one, the difference is this minus 2 here. Okay, it entered the equation by replacing y with y plus 2, okay? And that is going to be a vertical translation 2 units down, okay? So again, take that original function that they have provided for us and just move everything 2 units down. So again, your x-intercept, okay, will be down here. Okay, and again, just keep using all the same points that we were using before to draw the other graphs, okay? And you'll get a pretty good idea as to what is happening here. So like this, and through, okay? Like so. So there is my graph of y is equal to log base 3 of x, oops, I don't need a bracket there, of x, and then minus 2, okay, like so. Now, the questions, do any of the above transformations result in a change in the original domain or range? Okay, so basically what they're asking here is, do any of the graphs, the blue, the red, or the black that I drew, okay, change the original domain or range? Well, the blue one, okay, no, there were no changes there, okay? The red graph, there's going to be a change in the domain, isn't there? So the domain is now, everything was moved 2 units to the right. So before it was x is greater than 0, now it's x is greater than 2. Okay, x is an element of the real numbers. Okay, and for the black graph, or the third one that I sketched, no, there are no changes. Okay, so just moving the graph left and right changed the domain on the second function. That is it. State the equation of the asymptote for each part that I just did. So for that first graph, the asymptote was still the y-axis. For the second graph, I moved that 2 to the right, so x is equal to 2. And for the third graph, okay, it remained unchanged, so it was still x is equal to 0. Okay. All right. Last question here, you guys. Now, one of the laws of logarithms states that log base x to the n is equal to n log of x, okay? And again, remember, we called that our power law, okay? And we were working with that the last couple days. It says, however, okay, never a good term, are the graphs of y equaling log base x of n and y equaling n log of x identical? Are they the same? So they give us a little tip here. Investigate by considering odd and even values for n. All right, so what we're going to do is this. We're going to split our page into odd and even, like so. Okay, and what you can do is just draw a line right down the middle. Okay, and for each of those, what we're going to do is we're going to have some scenarios here. So I'm going to say n is equal to 3, n is equal to 5. Okay, and for each of those, I'm going to have 2 graphs that I am going to sketch. Okay, and same thing here, like so, and like so. And then for even, very similar scenario, I'm going to go n is equal to 2, n is equal to 4. Okay, and for each of those, I also want to be able to draw 2 sketches. Okay, and we're going to talk about these once we're totally set up here. Okay, now here's what happens. I'm going to start with the odd functions, and n is equaling 3. So if I take an n value of 3 and I substitute into the equation of the function, I'm going to get y is equal to the log of x to the exponent of 3. If I use the power law and bring that exponent down in front, I would have 3 log of x. Okay, now when we go in our calculator and I graph those, okay, you're going to see the same thing. I'm going to have a graph that looks like this for log of x cubed, and 3 log of x is going to look very similar, like so. When I go and I substitute 5 in there, I'm going to have the log of x to the exponent of 5, okay, and then I will have y is equal to 5 log of, 5 log of x, like so. And again, when I graph both of these, they will look very similar. Okay, they will both be identical. So at this point, you would say to their question at the top, are the graphs identical? Okay, based on what you saw there, okay, with the odd values of n, you would say, yeah, okay, they are the same. But here's where it gets a little confusing. When I substitute 2 and 4 into that function or that equation, here's what you're going to get. When I graph y is equal to the log of x squared, I'm going to get this function, okay, like so. I'm going to get 2 arms that go in opposite directions. When I move that 2 down in front of the logarithm, 2 log of x, I am only going to get this, okay? And the same thing is going to happen with the value of 4. So this is obviously a situation where I am discussing, and as you've seen, I've divided the page, even functions versus odd functions, okay, the values of n. So again, just finish this off, y is equal to 4 log x. Okay, so here is the reason why this occurs, okay? We know that for log functions, the domain, okay, is x is greater than 0, okay? I can't have negative values because if I take a negative value and I try and substitute in for x here or x here, we cannot have negative arguments, okay? We learned that very early on, okay, with logarithms. The arguments cannot be negative. So on this odd side of the chart that we're working on, no matter what I do, okay, I cannot put in negative values for x because it makes the argument negative. So in both scenarios here, okay, the domain is x is greater than 0, okay? No two ways about it. However, when I come over here to the even functions, there's a difference. For the graphs on the right, so the 2 log of x and the 4 log of x, okay, again, x has to be greater than 0, okay? I cannot put a value that is negative in there because it makes the argument negative. However, when I talk about x squared and x to the exponent of 4, okay, all that has to happen here, okay, the domain basically would be x cannot be equal to 0, okay? I can put a negative number into x squared and x to the 4th now because when you square a negative number, it is therefore positive. Same with any x to the exponent of 4. If I put a negative number in there, then it will also become positive. So for both scenarios, for the odd functions and for the even functions, when I have the number in front of the logarithm, the domain is still x is greater than 0, as it normally is. However, when you move that number down in front of the logarithm, if you are squaring your argument or putting it to the exponent of 4, 6, 8, etc., then your domain changes to basically just x cannot be equal to 0. And that's why the graphs will appear different, okay? Now, this is not a massive concept in the sense that you will see a lot of questions on this, but it does occur or does present itself if you are trying to solve things graphically by moving the exponent from the argument down in front of the logarithm or vice versa, okay? So again, I always promote solving things algebraically so you can see the solutions and see the calculations if they're valid or not. Your calculator is a good way to check or validate your answers, but again, be careful of this concept that we just went over here at the end of the lesson. It can sometimes cause headaches. Again, not a lot, but it is out there in your assignments and your textbook questions. Okay, so again, as always,